what is assembly theory, and how does it maybe play into the process in which you do novel drug discovery in computation?
Yeah, that's a good point. Good question. Assembly theory is a theory that explains causation from the bottom up, right? And it is causation is a funny thing because it's not supposed to exist in physics. So if you're a physicist, you'll say there's no causation, right? Which is kind of weird. Or that causation is an emergent property. Okay, so let's say that. In biology, causation becomes contingent because you have a thing called evolution. So what am I saying? So assembly theory, put in simple words, just recognizes the universe has a memory, and that memory is instantiated in chemical bonds because that's where you have enough diversity to store what happened in the past and then read it out in the future. So assembly theory just allows you to measure that memory, and then it allows you to understand how to interrogate that memory and use that going forward. Now, I built assembly theory in chemical space because in chemistry is the first place in the universe that things go combinatorial. And that means there's many possibilities and memories can form. And then, and applying assembly theory to chemical space allows me to basically figure out how I can go to novel forms of molecules that are not computable. And I mean, I said a lot in the last two paragraphs that the English words make sense, but there are so when I mean not computable, or have all the computer scientists who basically and the tech bros and all these go, oh, everything's computable, and is actually not. But that's a whole other podcast, probably a 10-hour conversation. But
Yeah.
the basic point is there are when I talked about the chemiverse, like you've got molecules, that space of known molecules. Then you've got known unknowns, things you should go. Then you've got completely unknowns. Those unknowns are not in principle predictable. And so assembly theory can help you chart a path into that unknown to fish out new structures that you can see are co-evolving with our biology as new angles for drug discovery. And that is a quantitatively different approach to drug discovery than anything else ever proposed by anyone else in human history. It could be complete nonsense, right? But I don't think so. And the reason I don't think so is I can use it to trace evolution um, processes in the cell and anticipate what molecules are needed. So that's how I'm using assembly theory in chemistry to basically get to novel molecular forms quite distant away from where we know them, and then check if they're useful to solve a problem.
Is there an example that you think you could give for that that would make sense for the listeners of how exactly you're applying some idea in assembly theory to reach into that unknown? Is there a practical
Yeah,
example that might be
yeah,
graspable?
yeah, really good one. And that is, let's take morphine or heroin,
Okay.
or take a drug. Let's take morphine. Morphine's a good one. So there are drugs that people get given for pain, chronic pain. And what happens over time is people become addicted to those drugs.
Yes.
And that addiction, if not managed correctly, can lead to dependency. And that dependency causes social breakdown. And I live in Glasgow and I travel a lot to San Francisco, and I know that
Yes.
Glasgow and San Francisco have had these problems. Actually, fortunately, they're getting lots less. Now, what is going on? Well, morphine is quite a complicated molecule. Um, to make the mission would be, one of my missions I've got, if I could do this, would be great. If I could make a drug that basically removes chronic pain, but is completely non-addictive,
Right. That'd be huge.
then we change the world
Yeah,
because
without a
human
doubt.
being. Now, the problem is that that molecule is likely to be really complicated. Now, morphine, if I was to make morphine manually in my lab from scratch, not to grow it, right, I would take 26 steps, right? That's the shortest way to get there. So if I wanted to investigate all of chemical space around morphine to make a new molecule, which was like morphine, but not quite as addictive, I have to invest time into doing 26 steps manually. It's
Right.
like building a railway, right? From, I don't know, let's say from Glasgow to the middle of the Highlands somewhere. And then every time, and I only take one trip and then I throw the rails away, never use it again. What a
Right.
huge, expensive mess. However, if I reuse the railway and go back to that station and build other houses for that village. Like, so you think of morphine as the main station. Then I go search around it using that railway. That's where computation comes into its own because I have the code to get to that special place, that morphine space. And then I just explore around it by making small adjustments. So I do of the 26 steps, I do 20 and then the same each time, a billion times. But the remaining 5 steps I do differently. So I make a billion complex molecule candidates like morphine, but not morphine, and I test them for addiction or not. And I think that's how now. How do we apply that? Well, assembly theory basically says, look, I can measure complexity by the shortest path recursively on a chain, right? It's just a chain of causation. That causation is related to biology by biosynthetic transformations or chemical reactions caused by biology. But let's not worry about that. Let's just imagine it's just like a recipe in a recipe book, and there's a number of steps in your recipe. The fewer number of steps, the lower the assembly index. The larger
Yes.
the number of steps, the more the assembly index. So I use the assembly index to count the number of steps and to go into different paths and project ahead and go, oh, if I add a couple of more steps in, I get a more complicated molecule. It's more steps, but it's more unique. And my hypothesis is you want unique molecules that are going to hit the precise receptor for pain and not hit the addiction one.
Yes.
And that's all we're doing. As a really good example, and I think we have a non-zero chance of actually finding molecules that will literally cure addiction.
Yeah, that'd be insane. I mean, completely insane. Does the assembly index have physical units?
It's just it does have in the assembly equation with the amount of assembly has physical units, has units of energy per unit mass, right?
Joules per
Um,
unit mass.
yeah,
Okay.
it's like kilojoules per mole, right?
Okay.
Now, the assembly index doesn't have units in itself, in that it's a dimensionless quantity because it just tells you the amount of information required, but you can measure it. And I mean, what it does, it has units of assembly index. It's like you're saying, oh, um, what's your, can you measure, there's this thing called temperature, you can measure it. Yes, well, what's the units of it? It's like, well, units of temperature. So the assembly index has units of assembly index.
Like, what I was curious about is, does it encapsulate a time dimension? Because it kind of seems like if it's capturing a historical trace, maybe you could say that something would be evolving over time in that measurement. Would that be
Yeah, yeah. Well,
accurate?
look,
Or
I'm working with a team in Arizona State University specifically on this, led by Sarah Walker. And what her insight into this is, like, the object is the causal history, and if you can dissect the object and work out how number of steps, that maps into a time because you need a minimum amount of time. So in a way,
yes,
the assembly index does has a it is its own unit, right? Assembly units of assembly index, and that itself is like a time because you need a certain amount of clock time or reaction time to explore that space. But
yes,
because the theory is under development, and keeping the fundamental axioms consistent is important, I'm a little bit vague on it because I'm literally inventing the airplane as it flies.
yes. But in, say, 10 years' time, you would maybe hope that assembly index has very well quantified physical dimensions grounded in, the language of physics or chemistry that we
Yeah,
use.
we can measure assembly index using spectroscopy right now. It's causing a
Yeah.
little bit of people going, because I'm saying, oh, it's the first measurable complexity metric. And everyone's like, no, that's not true. There's all these other things. And I mean, no, what I mean is assembly index of a molecule is an objective quantity that does not change as a function of the algorithm, right? It's the minimum amount of causation required to make the molecule, which is something really deep. And again, it can cause lots of arguments, which is cool. But yes. But the assembly index is part of the assembly equation, which measures A. And people are trying to say, what is A? Because the assembly index only gives you one part of the equation, right? It's also the copy number, the number of the molecules. Because if you were to make one really complicated molecule, You could make one really complicated molecule that use all the atoms in the universe. So let's take all the atoms in the universe, put them into one really massive molecule, and make the assembly index, the number of parts, as large as possible. The copy number would be one, right?
Right. Makes sense.
So if you were to instead say, well, I need to make identical copies of a complex molecule that has a kind of power, and the analogy I would give is like heat and temperature. So temperature is about the amount of, you know, the magnitude of energy, right? Like the assembly index, but the amount of heat is literally how much bandwidth you have, right? The copies of that power.
Yes.
I'm not explaining it very well, but it's like saying, if I had a big block of metal very hot and I wanted to cool it down and I used a small ice cube, even though the ice cube was at, just as freezing, it would not make a dent on the big block of metal because of
Yeah.
the heat capacity. So I'd have
Yes.
to have a lot of ice. So there are two quantities in assembly, the assembly index and the copy number, and those actually are related in the intrinsic physics of causation and mechanistically. And what I'm developing with Sarah and her team and my team is just ironing out the mathematics, because we've come up with a new problem in physics that needs to be solved. That needs to have conceptual grounding. And then we have to build the mathematical infrastructure around it. And I'm not a physicist or a mathematician or a computer scientist. I'm a chemist who likes burning molecules. Well, I'm actually not. I stopped burning molecules at sixth form. So now I like making molecules. So for me, it's kind of a little bit of a conceptually difficult but very satisfying
Yeah.
problem. And I've just got to chip at it step by step from first principles. And
Yeah.
then when people start to layer on information theory and other stuff like that, I just say, well, that's great, but does it help us in our understanding the phenomena? Like, what is the phenomena we're trying to study? And what assembly index says is how much causation, how much time, good point, and then and does that allow me to build new things and understand physical reality?
Yes. Does that mean that the human brain would be the highest assembly index system that we know of in the known universe?
Um, so it depends on which resolution you study it, because
Interesting.
no two brains are the same at the atomic level, right?
Right.
So that means the copy number is zero, right?
Interesting. Okay, because they're not
Now,
exactly the same system.
but that's now just that's but in the same way, if I had two molecules of methane, they would be in different vibrational states, and they might be different. But if you look at the correct resolution and correct the right features, so the question is, if I can find the right level at which to explore the brain and how the morphology is changed as it grows, then I think you will be able to count an assembly index with respect to a feature in every brain that's basically the same and therefore has a copy number, that resolution. And I think the short answer to your question is yes. I would say the human brain, or just the mammal's brain, dolphins, whales, whatever, would probably have the highest assembly index of any unit that in the universe we know of per unit volume. That doesn't mean that, say, language and other stuff, but then you've got to look at the infrastructure. You've got to make that autonomous, because a brain in an individual is autonomous. It can move around the planet.
Yeah.
And so you want to understand how much assembly per unit volume, per amount of stuff, per energy.
Really cool. I was speaking to a NASA astrobiologist last week called Amy Williams. She's worked on the Curiosity and Perseverance rover teams, and we were talking about these long chain carbons that were found on Mars. I suspect that assembly theory could be used to analyze those long chain carbons and sort of figure out if they were produced by life or not. Is that the right way to think about it?
Yeah, yeah. I mean, I think that NASA is doing a brilliant job to evangelize the possibilities for life elsewhere, but they're they don't have a metrology for life. So the
Yes.
problem with everyone, astrobiologists saying, oh, it could be this, it could be that, it could be the other thing. And so the problem with the long chain or molecule is it can be made randomly in high copy number, because there's not much causation. Just like add some carbon together and distill it, right? So so the question I would ask if I was a NASA astrobiologist is say, how many unique features does the sample have that can measure in any copy number to tell me how complicated it is, or better still, to tell me the assembly. And so I would guess that Mars right now is quite dead. And so I'd say those chains of molecules, they're unexpected because astrobiologists weren't looking for them and they weren't thinking about them. Like every time we find a new thing we weren't expecting, we go, oh, evidence of life. But actually you have to say, no, did evolution produce that object? Can we tell? How much time, how many parts? And if we can't tell, then we just don't know. And so what I'm trying to shift at NASA to do is to use assembly theory. So when it goes to Titan with Dragonfly, with its mass spectrometer, it can apply assembly theory. Now, does it mean there wasn't life on Mars? No. I'm sure there is every possibility of it. But if there are remnants of life, detectable remnants of life on Earth, on Mars, where you can actually, where it can actually know, given the data, that life produced that object, you might have to dig down a bit on Mars, but that'd be really exciting. And I think NASA astrobiologists are doing the right thing. But no, oxygen, finding small molecule. Basically, what I'm trying to say, finding small or repetitive molecules that are unusual might be what I call is a hint
Yeah.
of life, but is not a proof of life.
Yes.
Right now, some melodramatic, I won't say anyone negatively in this. I've already talked about people positively. Astrophysicist is saying, oh, there's a thing moving around the solar system that's emitting nickel vapor, and that's the proof of alien intelligence. No, it's proof that there's nickel tetracarbonyl, and nickel tetracarbonyl is like nickel, and and what we do in chemistry is we take carbon monoxide, CO, which is related to CO2, and if we bind it to nickel, you can make a gas of nickel. We do that in the lab, and it's quite unusual. And the fact we see this object degassing nickel, which means it must be nickel tetracarbonyl or something like that, everyone's going to alien. It's like, no, it's got 3 atoms in it. Nickel, carbon, and oxygen. That is simple. Like water has 2 atoms in it. Well, sorry, water has 3 atoms in it. It has oxygen, hydrogen, and 2 hydrogens. Where nickel tetracarbonyl basically will have 9 atoms in it, right? Because you've got 4 times 2 plus 1. But anyway, who am
But
I?
does the rarity of the element not vary there? Like you could have a 3-molecule compound that contains an incredibly rare element, and then a 3-compound molecule that contains only very common ones, and they might have the same assembly index, but obviously they're very different because one of them has an extremely
The
rare.
copy number will capture that because rarity is about abundance, right?
Yeah, makes sense.
That's why assembly theory works.
The copy number makes sense. Yeah,
the copy number is the most important thing in assembly theory,
right?
Right. The copies are the most important thing in the universe,
So
particularly if they're weird things.
Yeah, no, that makes complete sense. So if you were head of NASA trying to find extraterrestrial life, how would you implant the assembly theory onto these rovers to find extraterrestrial life? Like how would you go about it?
There's probably 4 or 5 things I would do. The first one is I would basically build the next generation of space telescopes to look for a high resolution infrared, to look for structure in the infrared. So you can do that because you can count complexity in the infrared. But if I was local with a rover, I'd have a mass spectrometer. Well, the nice thing is they're sending out infrastructure with the basic ability that we need, right? So that's good. So I would maybe think about how I could work out how assembly theory would work in time series data. And my collaborator, Sarah Walker, she has a student who's looking at assembly theory on exoplanet atmospheres, right? And right now, I mean, they've got some data that shows from space they can detect the difference between technological part of the planet and a biological part of the planet and a dead part of the planet. Desert, Amazon, urban China.
Wow. And this is from
Right.
obviously,
From space observations.
very long distance away. So explain how that's working. They're using a mass spectrometer, kind of shooting some sort of energy into that atmosphere. It's ionizing.
So that would use infrared spectra. So you use light. The mass
Okay,
spec so mass spec is local. You'd like a nose. So on a rover, you'd use a mass spec. From orbit, you'd use a laser, a kind of camera of some description, right, to get energy in and to read what comes out. So
right.
so I would do that. I would also the other thing I'd do is I would actively stop anthropomorphizing, looking for DNA. Because DNA, the only place in the universe that DNA exists is planet Earth.
Oh, you can't say that for sure.
Yeah, I can. And
You're
well,
almost
for
certainly
sure.
right, but you can't say for
Well,
sure, right?
well, for sure. No, I'm going to qualify that. I'm 99.99999% sure. I'm not 100% sure. No, because of obviously probability and so on. So what do I mean? I mean the chain of events that needed to make DNA was
Yes.
so contingent on Earth. There were other possibilities. That doesn't mean there aren't DNA-like molecules everywhere in the universe. They might have a different methyl group or slightly different feature. So they'll be almost the same, but
Yeah.
not. And basically, the precise features are contingent. There is no magic in biology, right? People
Yeah.
think there is one way to do biology. There's more than one way to build a car, right? And it's a bit like you imagine if you build let's say you take your favorite car and you drive around the world and you get dents in it. And then you would just do that again. You take the same trip and you get dents in it. And you look at your two cars, dents will be in different places because there's a contingent, because different things happened. So what I'm saying when I make the dramatic statement that DNA doesn't exist anywhere else, I'm saying the precise features we have associated with our DNA, the molecular
Yeah.
structure, the helicity and all that jazz, it is very, 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 very unlikely that will be adopted elsewhere unless there's a common chemical origin and some contingency. It would be really cool if we found there was life on Mars, number one, and we found the life on Mars was almost the same as life on Earth, but there were certain differences that we could trace back to the chemical evolution where things were slightly different.
Yes.
That would be great. And then if we went to the outer solar system, we found life, and we found that life was different there, like a not a second genesis, an alternative genesis to life in the inner solar system. That would be also super interesting. And so what I would just tell NASA is to stop obsessing. Let's stop just basically going, oh, it's going to look like that because of what we have here, and start building theories that are based upon the scientific method and good philosophy. Right
Yes.
now, our astrobiology is a discipline. I wouldn't want to be an astrobiologist because it's a bit like being I don't know, a cosmopsychologist. It's like, what's that? It's like, well, I think the cosmos is alive, and I'm gonna assess the psychological state of the cosmos. I'm like, really? You know, astrobiology is a hell of a discipline because there's no observations, right? And so most astrobiologists are encompass a wide spectrum of people from planetary science to maybe biochemistry who want to apply their tools to looking for biology elsewhere. That's fine, but they have to understand that their tools looking for biology elsewhere are not appropriate. And
Yes.
the entire discipline is going to have to reformulate and say, well, what is the theory for life in the universe? How does life evolve in the universe? And then what does exobiology look like? I wouldn't call it astrobiology. That's a strange term. Exo life is probably better because biology is by definition what we know on Earth.
Yeah. Yeah.
Why we
Makes
say
sense.
astrobiology? Even the term doesn't make any sense. No disrespect to Emily, who's awesome.
Yeah. The giant news. We created a completely free ebook titled 26 Neuroscience Books for 2026. I've read over 100 neuroscience books in my life, and with Christmas just around the corner, I thought I would help people find the perfect book for them or to buy for someone in their life. It includes really nice science-based illustrations, an accessibility guide, and personally written segments for each book and the impression they left on me. I also asked 100 top scientists like Dr. Mike Levin, Anil Seth, Nick Lane, and many many, many more what their favorite science book is, and you can find all of those included at the end. If you want to support the channel, you can also purchase a beautiful physical paperback copy, also a perfect stocking filler. We put a lot of effort into our first Giant Shoulder product, and we cannot wait to hear your thoughts. Check it out in the link below. Again, it's completely free.